Oh, you're here. Very good. All right, we are on. All right, guys, this is an exciting day because we're officially starting our AP review for the AP exam, which is 1 month from tomorrow. I have a belief that you have to go through 5 AP exams, not get them all right, but understand what you didn't get, like go through them, practice them, and understand and go through the corrections to get a 5. That's just my sense of it. That's how much practice it takes. Yeah. Okay. You have 4 items on your desk. One is this with the do now. You should have 4. You don't? Oh, let me pause this. Okay, so what you have in front of you, you have the 2008 multiple choice. Now there are 2 sections, but 1 through 28, that's the no calculator section. That's what we're going to be working on today, and you're going to finish for homework. 28 multiple choice questions without a calculator. Well, we're going to try. So the more we get done in class, the less you have for homework. Now, so you do know that I have it as the first tab on my e-board, the 2008 multiple choice. This is an actual exam that was given. If you click on my e-board on the tab, there's a video explanation for each one if you get stuck and you want to know. Okay? So the other thing that you have in front of you, you got a couple of things other than the 2008 exam. You have like a guide that tells you basically what you need to be able to do, all the major tasks. That's also stapled. When you see, then you do this. And the other thing explains to you the format of the AP exam, how you're going to get 50% of your points from the multiple choice and 50% of your points from the free response. So that just goes over the format. Okay, but let's get right into this then. We're going to look at these limit questions. Try the first one if you haven't done so. Did we get an answer yet? What did you get, Ryan? You got 6 also? What did you guys do to get this? Because when you first try to plug in the 3, what do you get? 0 over 0. So then one way to do it is you factor, cancel, and then substitute. And you do get 6. Now, guys, I want to tell you now, it's not part of the AB curriculum, about something called locales. Something, yeah. Oh, yeah, that's right. When you get 0 over 0 or infinity over infinity, I'm going to show you another way to get the limit. It's real quick. And you're going to say, why didn't you show me that before? I just didn't feel like it. Okay. It's not in the curriculum, but it works. What happens when you get 0 over infinity, what you can do to get the limit is keep the limit as x approaches 3, but replace the numerator with its derivative. What would the derivative of x squared minus 9 be? 2x. What's the derivative of the denominator? Now try to plug in the 3. Anytime you try to get a limit, you get either infinity over infinity or 0 over 0. You can just replace the numerator with its derivative and replace the denominator with its derivative and try again. Sometimes you got to keep doing it until you get what you want, until you get an answer. Okay. So yeah, but normally if x is approaching a constant, you try to plug it in. If you get 0 over 0, factor, cancel, substitute. Okay, try the one underneath it. The rest are with infinity or negative infinity, so we got to look at the degrees. Are we thinking anything about this one underneath? X approaching negative infinity? Yes, Gina? It is 0. Now, did you compare the degrees? The numerator? Yep. So, but only do that when x approaching positive or negative infinity. One way to get the limit is compare the degrees. If it's less than the numerator, it's always 0, which means you have a horizontal asymptote, y equals 0. Yes? Nope, not with that. But the other way you could have done this with our friend Mr. L'Hopital is if you try to plug in the negative infinity, you'd have negative infinity over infinity. You would be allowed to try it again. You can replace the numerator with its derivative. What's the derivative of 4x? What's the derivative of x squared plus 4? Now, if you try to get the limit, you've got a fraction, the numerator's staying at 4, the denominator's going to negative infinity, right? What's 4 over negative infinity approaching? 0. Anytime it's a constant over infinity or negative infinity, it's 0. So that would be another way of doing it. Alright, next one. The limit as x approaches infinity of x over x minus 2. Cameron. 1. How'd you get it? Yep. It's just the ratio of the leading coefficients if the degree of the numerator is equal to the degree of the denominator. Easiest way to do it. But again, you could use L'Hopital's. You'd be finding the limit of 1 over 1. How do I, the way he did it? Oh, L'Hopital. Yeah. Yeah. It's a French name. Yeah, it looks like the word hospital. Yeah, with an L. Alright, now the last one. Limit as x approaches negative infinity. Again, what do we think about this one? Technically, it doesn't exist. Now, what if the choice does not exist, isn't there, and one of the choices is positive infinity and one's negative infinity? How are we going to determine? That's right. You know when the degree up here is greater, that it's going to be either positive or negative infinity. Yes? They would never do that. They always put one or the other. And the thing is, when the degree up top is greater, technically the limit doesn't exist. But what it's saying is that your graph, as x's go to negative infinity, either they're going to go up or they're going to go down the y coordinates. So the way you determine which one it is, you look at the sign of the leading terms. And if x is approaching negative infinity, the numerator is negative. Because a negative to the fourth is, what did I say? Negative? Positive, I'm sorry. A negative to an even power is positive. And the denominator, the leading term, is 3x squared. And as x approaches negative infinity, that's also positive. So that's why it's positive infinity. If this had been an x cubed up here, then it would have been negative infinity. It would have been an x cubed. All right. So that's a little warm-up. Psyched? Yes. There's a slant asymptote when the degree in the numerator is exactly one more than the degree of the denominator. Right. Yeah, you don't really have to worry about slant asymptotes in here. All right. Well, what that tells you, if the degree is one more up here, if it was an x cubed, basically the graph's going to look like a line when you get towards the ends. It's going to look like a linear equation. All right, so we are starting. First question is a limit question. Oh, go to the 2008. Sorry. Okay, so who's got an answer for me? Just wait a minute. You have B, which is what's the number? 2, right? Did everyone else get that? Okay, tell me how you did it. Did you multiply the entire numerator and the whole? Did you? Yeah, because all you care about is the leading terms, right? When x is approaching infinity, so you really only have to multiply the highest power terms to see. Oh wait, did you say negative 2? Yeah, it's going to be negative 2. Because if you were to multiply this out, all you care about the leading term. So that's all you. Now the degree is the same. So So you take the ratio of the leading coefficients to get the limit, and it is -2 over 1. Your first question done. So exciting. All right, so now you can try the second question. Oh, easy breezy. I hope. Yep. At 3, because I know that's bugging you guys. Okay, so for this one, for number 2, you can use the power rule if you bring the exponent up, right? What did you guys get for this? D is at -x to the -1? Yeah. You can only integrate x to a power if, other than -1, if you bring it up. Now we add 1 to the exponent and multiply by the reciprocal. Now, if they didn't have this choice there, you would have rewritten it as -1 over x plus c. Do we like that one? That was a nice straightforward one. All right, then we're going to get to 3, and that's where it all starts just to unravel. Okay. Well, 3, the first thing you should have done is the product rule, and you should have got to this point. First times derivative of the second using the chain rule, plus the second times derivative of the first is just 1. Now, very often with the product rule, they'll pull out the GCF, and if you look, the terms are separated by the plus right here. So in the first term and the second term, they both have in common a factor of x squared plus 2 squared. That's what you want to pull out. Now, so you have this beautiful first factor, and the second factor, it's like your leftovers. It's what's left after you pull out the x squared plus 2 squared. You want to clean that up. And if you do that, the first term, if you distribute your 6x over the x minus 1, you'll be able to combine it with the x squared plus 2. If you distribute the 6x over the x minus 1, you have 6x squared minus 6x. And you can combine the x squared and have 7x squared. So is that D, guys? I'm not sure. I don't have a D. Was that bad? No. Now we feel silly saying that was bad. We've been GCFing since we were 8. Alright. Now, you ready to look at 4 together or no? Did you try 4? Yep. You're trying it right now? Let me just see. This is what I have here. Okay. Now, when you go to integrate a sum or a difference, you can just do them separately. Right? So you want to integrate sine of 2x. It's not just sine of x, it's sine of 2x. So it's a little u substitution. And if you want to integrate sine of 2x, what would you need sitting right next to it? A 2. And if you put a 2 next to it, you need a half out front. So for this first integral, you have 1/2 the integral of sine u du. You just got to make sure you always have the derivative of the inside function sitting there. And then you got to know what the antiderivative of sine is. It's negative cosine. So you'll wind up with the half, a negative cosine of 2x. Yep, yep. Now, if you got that one, there was only one choice that had negative 1/2 cosine of 2x for the first term, which was nice. You didn't have to go to the second term. You could have integrated the second term too. Yep. Correct. Yeah, that just comes up when you have perpendicular lines, like write the equation normal. That's negative reciprocal. But with u substitution, you just want to put in the reciprocal so you don't change anything. Sydney, yes. You don't get why it's u sub. But let's just look at the first integral instead of the second one. So one of the things we're going to have to do is integrate the sine of 2x. Right, that's the first term. We know that the antiderivative of sine of x is negative cosine of x. But if it's anything else, not just an x, it's u substitution, and we let u be the inside function, 2x. So in order to integrate the sine of anything other than x, you consider it u, and then du the derivative of the inside is 2. You need that to start. So if you put a 2 in there, you multiply by something that wasn't there before, you need to multiply by a 1/2 on the outside. So what I have now is 1/2 the antiderivative of sine u du. Now, yeah, see, I'm not doing all the u's and converting it before, but you definitely can. So I have 1/2 negative cosine u, or negative 1/2 cosine u. And if you put the u back to 2x, you have negative 1/2 cosine of 2x for the antiderivative of the first term. Now, if you were ever really stuck and you had to find an antiderivative, take the derivatives of the choices, right? You find the choice that when you take its derivative, you get the original integrand. You work it backwards, right? Does that make sense? So if you go to choice, what was this, choice B? Yeah, if you take the derivative of it, you'll have sine of 2x plus cosine of 2x. You're stuck, you know? Okay, so now I think I have to let you have time. Oh, it's a limit one. And it's 0. You can try plugging it in. It doesn't work. It's 0 over 0. So either factor, cancel, substitute, or use L'Hopital's again and again and again. So you don't get 0 over 0. All right, let me give you a little time on this. Okay, number 5. X is approaching a constant, so you try to plug it in. You plug in the 0, you get 0 over 0. Oh no. That's indeterminate. So what did you guys do to get this one? Factor, cancel, substitute works easier on this one. So if you factor out the x squared and cancel it, but don't forget, then you still have to substitute the 0 into the reduced form, and you get 8 over negative 16, which is negative 1/2. Good one? If you did L'Hopital's, you have to keep going over and over. It takes 2 minutes. Okay, number 6. Okay, I like the order that these are in, because if it can only be continuous if the limit exists, and it can only be differentiable if it's continuous. So that's why we got to start first by checking if the limit as x approaches 2 exists. Now, what was a little weird about this, they didn't make a separate branch for when x is less than 2 and when x is greater than 2. You use the same branch to find the limit of this function as x approaches 2 from the left, as you do to find the limit as x approaches 2 from the right. And for both of them, you're using the same branch. So you're going to factor, cancel, and substitute. And either way, you're going to be plugging 2 in, and what do you get? You get 4. So it's going to work the same way when x is approaching 2 from the right. You're also going to get 4, which is not a big surprise because you're using the same. Yeah. So the limit as x approaches 2 exists, and it equals 4. What that's telling you, that if you have this graph, as the x coordinates approach 2, the y's are approaching 4 from both sides. Yeah, for x is less than 2 or greater than 2, you're using that top branch. Now, you want to see if it's continuous at 2. How do you know it's not continuous? Yeah, f of 2, it's 1, it's not 4. So you got the point down here. In order to be continuous, f of 2 would have to equal the limit of f of x as x approaches 2, and it doesn't. Yeah. So the fact that it's not continuous, I don't check to see if it's differentiable. It can't be. Okay, it has to be continuous to be differentiable, and it's not. So you don't check that. So it's only A. Yep. 1 only is A. Yep. Then the next step, and it wouldn't look like this, you would write f prime of x, you take a piece of piecewise function for the derivative, you would plug the 2 into each branch to see if they're the same. We'll do this last one together, and then the rest will leave you. They give you the velocity. They tell you the position at time 0 is 2, and they want it at time 1. So what did you do? Yes. Yeah, because. Mhm. Mhm. No, yeah. So yeah, the velocity is the derivative of the position. Sometimes they use x for position, sometimes they use s. But yeah, the first thing you had to do here was take the antiderivative of velocity, and you don't want to forget your plus c. And then they told you that the position when time is 0 is 2. So you put in 2 for the position, 0 for time. That allows you to solve for c. Once you know your position function, then you can get the position at any time, including 1. You just plug in 1 and you get 6. Yes? No? Yeah? Okay. So you're going to try for a homework, you're going to try to do as many of these other no calculator questions. Do it without a calculator. Do you see anything in there that you think it's going to be trouble? Big trouble? 13 looks like trouble? Yeah. Let's see. So 14, sorry, I'm just looking at your step. They give you values of the second derivative. All you know is the value of the second derivative. You don't know what's going on between points. Now, you said you thought that it looked like a couple of them were going to be true? D and E? D and E. 14. Sorry, I took yours. 0 to 2. Well, what would happen though, like if the second derivative went up to 0, went down to 0 at 1, but then it didn't go negative. Then like at 1.1, it was a little positive again. So you have to know for sure. Yeah, realize it can do anything on either side. I think there was a question on 13 too. I just want to grab this one more time. 13, 13 guys, that's just chain rule. You're taking the derivative of a composition of functions. So I'd substitute in the ln of x for x first, then just take the derivative. And which one did you say, 16? 16 is implicit differentiation. When you take the derivative of the inside, use that product rule. Use the product rule.